When you think of Earth, you probably think about your own life on the planet and what you do in your day-to-day life. But what would happen if the Earth we knew now was suddenly affected by outside forces bigger than any world power could stop?
According to NASA, the Milky Way galaxy in which our solar system and Earth resides is on a collision course with another galaxy, namely the Andromeda Galaxy. Out of the two, the Andromeda is slightly bigger than the Milky Way, which creates a problem for us. What would happen if the Andromeda and Milky Way collided?
Before we talk about the consequences of these galaxies' eventual meeting, let's do a quick recap on what exactly galaxies are. Galaxies are a gravitationally bound system made up of stars, star clusters, gas, dust, and dark matter. Other objects such as planets, asteroids, and comets are also common. They're usually greater than 1,000 light-years across and recognizable as a discrete single object. There are usually many stellar systems in one galaxy, like our own solar system.
Galaxies also come in many different shapes and sizes. Because we primarily see galaxies from Earth's viewpoint, galaxies appear to have many different forms. However, there are only three major classifications of galaxies. The first type of galaxy is the elliptical galaxy. Elliptical galaxies have a circular or elliptical outline in space, containing no disk and a population of old stars. New stars rarely form here, but these galaxies typically contain trillions of stars. They're also classified from E0 to E7 based on their relative evolutionary stage measured by how flattened they are. Some examples of elliptical galaxies are the IC 1011, one of the largest galaxies that we know of, and the Sombrero Galaxy.
The second type of galaxy is the spiral galaxy. Spiral galaxies have spiral arms that lay in a disk, hence the name, and are classified into two types, normal spirals and barred spirals. Both have a central bulge, which looks similar to an elliptical galaxy that extends above and below the disk. However, barred spiral galaxies have a central bar-shaped structure. Spirals typically have less stars than ellipticals, ranging from 10 to 100 billion, but have a similar classification system, with types A, B, and C, to determine how prominent a bulge is and how tightly the arms are wound. Our very own Milky Way and the fast-approaching Andromeda both are barred spiral galaxies.
Some galaxies combine properties of both elliptical and spiral galaxies. These galaxies are known as SO galaxies or lenticular galaxies. Galaxies in this category have a bulge and a disc-like spiral that's characteristic of spiral galaxies, but the smooth appearance of an elliptical galaxy. Galaxies in this category are also classified by whether it has a central bar structure, or if it doesn't. Similar to elliptical galaxies, lenticular galaxies have very little star formation within them. The Cartwheel Galaxy is a brightly colored example of a lenticular galaxy.
If a galaxy doesn't fit in with a spiral, elliptical, or lenticular galaxy, it's classified as an irregular galaxy, the third classification of galaxies. Irregular galaxies lack symmetry in shape and structure. Many of these galaxies were once originally normal spiral or elliptical galaxies that became distorted due to the gravity of another galaxy. Even though irregular galaxies don't have specific classifications because they're all unique, there are three major types. Ur-1, where the galaxy has some structure reminiscent of other kinds of galaxies. Ur-2, where the galaxy has no recognizable structure. And dwarf galaxies, smaller galaxies with lower luminosities than larger galaxies. A very close example of an irregular dwarf galaxy is the small Magellanic Cloud. Astronomers speculate that it was once a barred spiral galaxy, but because the Milky Way disrupted it with its attractive pull, the galaxy became irregular. Maybe this gives us a little hint about our eventual fate?
Now that we know about the different types of galaxies, let's learn about how galaxies move, because in order to prepare for our eventual battle with Andromeda, we need to be able to predict how long we have before the time comes. Ever since the Big Bang, space has been expanding outwards at an increasing rate, so it's probably more accurate to say that all galaxies are moving as a result of space expansion rather than because of the galaxy moving with its own velocity. This property of space is also known as Hubble's flow, which applies to galaxies that are far from each other and will expand with the universe independent of the effect of the other galaxies.
But what happens with galaxies that are closer together, like Andromeda and the Milky Way? When two galaxies are close enough, instead of expanding outwards with the universe, they instead pull each other closer because of their own gravitational pulls. We know that Andromeda is moving towards us because of the presence of blue shifts of the light emitted by Andromeda. This effect is known as the Doppler effect. When a source of light waves head towards you, the wavelengths become shorter, leading them to become blue shifting. Light heading away from you has more longer, spread out wavelengths, which cause them to become red shifting.
While Hubble's flow states the majority of galaxies are moving away from us, there are a group of galaxies that are gravitationally bound together, which are known as galaxy groups. Think of a galaxy group like your personal friend circle in the middle of college, except that your circle can consist of up to 100 members. In the Milky Way's galaxy group, known to us as our local group, there are the Milky Way, the Andromeda Galaxy, a few smaller elliptical and spiral galaxies, and a lot more smaller dwarf galaxies. The third largest galaxy in this group, called Triangulum, is an unbarred spiral galaxy that is at most only a few percent the mass of the Milky Way or the Andromeda.
Just to give you a mental picture to help understand how big our galaxy is, about 98% of the local group is made up of material from either the Andromeda or the Milky Way, with the other 50 galaxies or so making up the other 2%. If a galaxy group takes up enough space, it can become a galaxy cluster, and occasionally galaxy clusters can bunch up together to create superclusters. Our own local group is part of the Laniakea supercluster, and within the supercluster is a galaxy cluster called the Virgo cluster. That's a lot of clusters.
So what will happen in our stellar clash that's taking place approximately 4 billion years from now? Well, the good news is that since a majority of the galaxy consists of empty space, there won't be a majority of collisions, bar the few gas diffusions that, upon collision, will cause hot shocks. Many of these dust and gas clouds in each galaxy will combine to form more stars, and would take about 2 billion years for the Milky Way and Andromeda to combine into the eventual Milk-Andromeda Galaxy, which would take the shape of a giant elliptical and not a spiral like the original galaxies because of the influx of new stars and the death of older stars.
It would take around 6 billion years for the process to be completed if we started counting today. Will humans still be around to witness the merging of the two largest galaxies in our group? The Sun, which provides energy for life on Earth, will eventually run out of helium to fuse in about 5 billion years, which occurs after the initial collision of Andromeda and the Milky Way. Before then, it's likely that humans would either have moved on to a different planet or stopped existing altogether. We're all minuscule components of the universe, almost irrelevant to the cosmic events in the distant future. The most we can do as humanity is watch as it happens and hope we survive long enough to continue life on an inhabitable planet. Maybe then we can witness the true end of our origin.